So say it's yeah. So this one I don't. Like this? Yeah. It's good. All right. Good afternoon, everyone. Hopefully you have a good lunch. Any questions for the material we discussed in the morning? Any questions before we continue? Okay. All right. So yeah, I guess in the morning we basically talk about what is IPCC, right? So what do they do, and what's the history of IPCC, and then we talk about some basic concepts of climate science. What is basic concept about climate change, right? So why we use anomaly, right? Not absolute observations, right? Why we care about the uncertainty, how IPCC deal with uncertainty, right? So what is CMIP, right? What CMIP 6, things like that, right? So then we'll, in the afternoon, we'll continue to talk about some of the key IPCC findings, right? So like mentioned, the whole report is more than 2,000 pages. So we won't be able to, cover all of them. We can just pick a very small proportion, I think quite important and quite relevant to us. So again, this is IPCC report, the first chapter. So for this lecture, we'll basically talk about what are the major drivers in our climate system and how do we know them. What other ways people measure the changes. And when we think about the Earth's energy balance, right? So the two important things, the Earth, the source of the energy is actually from sun, right? From the solar energy, right? So that's why when we think about the changing climate, we have to think about whether the source is changing, whether solar radiation is changing. And also we talk about positive and negative radiative forcing, right? So for the greenhouse gases, their radiative forcing is positive. But there is one big player in our Earth's energy system, that's volcano forcing. So that one is a negative radiative forcing. That means they are cooling the climate, right? So when we think about the changing climate, we have to think about how solar energy has been changing and also how volcano activities has been changing in the past. So this is from IPCC report. On the left, we are talking about the solar radiation change. In the top one is in the last 2,500 years, and then the bottom one is the last 150 years, more recent change. And on the right panel is basically, we are talking about the volcano forcing. On the top, again, is the long-term trend. We are talking about the 2,500 years. And then the bottom is about 150 years. So let's look at the left one first. That's the solar radiation, right? What's the general trend you will see in the last 2,000 years and the last 150 years? Is increasing or decreasing or no change? We're talking about this one. It's not a tricky question, right? So we're just reading from the figure.
There are three patterns in that graph.
You're talking about here, right?
In 1900, it's constant. Then it is increasing. Then again, 1900 it's increasing.
Okay.
Constant.
Right. So yeah, if you look at the 2,500 years, right? So it's relatively stable, right? So there's not a huge change. But when you look at the last 150 years, there is a slight increase here. But when you put into the context of the long-term history, you will see the change is actually not huge. Even it look like there is an increase. But when you put this part of the increasing trend into the 2000 years, there are times like that magnitude, right? So that is IPCC conclusion, right? So basically, in the last 150 years also, yes, they're a little bit higher compared to maybe here. But when you put into the longer context, it's not like a huge change. So that's basically the IPCC conclusion we have about the major driving force of our climate system, right? So that is the ultimate source of energy for Earth, right? So essentially what I'm talking about, essentially they are quite flat, no huge change. How about the volcano activity? What?
I just want to know about the figure A. If you look at the scale of the valleys, it seems very small.
Right, yeah. So you mean the changes are very small, right? Yeah.
Can it be attributed to some errors? I mean, we are measuring something, we are measuring the indicator, right? Some senses or some observed data, and then we are plotting it. So the scale on the y is very small. So what about the stability of that data? And will that be error free?
Right, that's a good question. Yeah, so basically we are talking about the number, the change in number is very small, whether we can make good enough measurement, right? So yeah, that's a good question, right? So that's basically, right now what we are measuring is using satellite, from, we can directly measure the radiation outside the Earth without influence of Earth's like atmosphere, right? So it's very accurate. We know that. And but when we talk about the 2,000 years, really you actually use a proxy, right? You use not direct measurement. You are right. So there's some uncertainty in terms of the proxy. But again, people try to use the same proxy and then calibrate that with the most current, 30 years, 40 years measurement. And you can see the calibration is very good, even with a small number, because they don't, energy measurement is not that hard, just like temperature, right? So it's actually, you could measure them quite accurately. So, but you are right, we are really talking about a very small change, right? But again, that's a point, really the change we are talking about, you can say is really less than like 1 watts per square meter, right? Out of 1,300 watts per square meter, right? It's relatively small. So how about the volcano forcing? What's the general trend? Is it increasing, decreasing, or no obvious trend? So remember this one we talk about, that is only negative forcing. Really major negative forcing in our Earth system, like a cooling Earth essentially. So what the trend tell us in general? Increasing, decreasing, no trend? So this is what IPCC put, right? So I guess, in summary, essentially what I talk about, there are basically variability, but there is no like obvious like increasing or decreasing trend. It's basically in the last 2,000 years, it has been relatively stable, right? So because volcano activities, as we know it, is random events, it's not like there are, like a frequency we can describe, right? So in the last like 150 years, sometimes there are big ones, like we talk about, the one in Philippines, right, 1997, right? So it's a big one that's cool the Earth's temperature for almost a year, right? So that does impact Earth system, but Earth system like energy balance. But when you look at the long-term trend, there's no like a clear trend. So I guess really the key message here is when we talk about the climate change, right? So what's really driving climate change is not from solar activity. It's not from volcano activity, right? So that's really the key message. So really what happens, we know, is what happened in the Earth's atmosphere, right? The greenhouse gas are changing. That's actually the major cause of our temperature change. So when we think about the greenhouse gas in our atmosphere, right? So Earth has a long history, right? So it's actually there are different periods. There are actually Earth has a very high CO2 concentration, much higher than what we have now, right? So we'll look at 3 figures, like 3 pages of Earth's history in terms of greenhouse gas. This page we will see like a deep time, right? Geological time. You can see it's 450 million years old, right? So we talk about really like ancient time. We zoom in to like the recent 60 million years, and then we zoom in to the last about the 3 million years, right? So that's what look like. So this one, of course, you can imagine that's not direct measurement, right? So we don't have a CO2 number, from that time. So what people does is actually using the geochemical proxies, right? So that's called a foraminifer, right? So that's a small living creature lived in the ocean, right? So their shell is a carbonate. So carbonate has oxygen. Oxygen exchange with CO2. So you can actually refer to the CO2 concentration, right? So people collect them. They are very small. You can't really see them from naked eye. You have to use a microscope, blow up, and you'll be able to see them. So people use this type of a chemical tracer to be able to refer what CO2 level in Earth has been in the deep time, right? So you can see essentially there are periods we have a very high CO2 level, but in general what we saw here is from around 60 million years old, Earth's CO2 level has been dramatically decreasing, right? So that's really the overall trend, right? So Earth has spikes, but in the last about 60 million years, the CO2 level has been slowly declined, right? And then when we move to more recent history, right? So we are talking about less than a million years old. So these are the almost direct measurement, right? So these are the ice core measurement, right? So basically, you have the gas trapped into the ice core, in Antarctic, and also in some glaciers. So people can, extract air out and then measure the three major greenhouse gas directly from ice cores. Right? So that is a direct measurement of the concentration of greenhouse gas in last 800,000 years, about a million years. Right? So basically what we saw here, there is a fluctuation of all 3 gases. Right? So that is basically the glacial and deglacial cycles. Earth has many of these cycles, right? But in general, it's also stable, right? In last million years, the greenhouse gas concentration has been stable. Really, what happened is in the last 150 years, since the start of industrialization, right? Since we start making use fossil fuel intensively for our industry purpose, life purpose. So CO2 and methane and 2O has been dramatic increase. Right? So that is ice core measurement, more recent history. And then we have a more direct measurement, right? So really just the modern measurement, really we measure exactly how much the concentration. So again, even this one is kind of a direct measurement, but you actually measure from the air bubbles, right, in the ice core. And this one is actually directly measure the CO2 concentration in the atmosphere, right? So these are so we will talk about each individual one separately. But here I just give you the major sources of different measurements. So the key message here is there are different groups in the world. They actually directly measure this CO2 gas or this greenhouse gas, right? So there, for example, the first one is you don't need to remember the acronym, but essentially that's NASA, the agency of NASA. They basically measure greenhouse gas. So another major one is from NOAA. So NOAA has a global network, they try to measure the greenhouse gas. When I do field work in Africa, like I remember that's one very remote research station in Namibia. So they actually help NOAA. They are one of the NOAA monitoring site. Every month, people actually drive the car deep into the desert, use flags from NOAA and fill the air and then ship to NOAA. NOAA will measure this. So these are like NASA or NOAA is kind of a government-sponsored program. They try to continue measure greenhouse concentration in the air. And then there are some university ones. One is from University of California, San Diego. Right? So that's from Scripps Institute of Oceanography. Right? So that's is famous for their oceanography program worldwide. So they keep measurement of greenhouse gas as a global scale. Another one is from University of California, Irvine, UCI. So they, from their Department of Chemistry, they have a program has been continuous running the greenhouse gas in the air. Right? So there, basically the idea is, so that's are the major sources of IPCC report. Where they get the data from is from these different sources. Right? So in the map actually it's showing the different sources. You can see they almost matching each other. Right? So give us confidence. Some are government-sponsored programs, some are just the university-sponsored program. So they give you similar answers. So we'll talk about major three major greenhouse gases separately. Right? So the most major player we know, of course, is the CO2. Right? So that is a major reason for our Earth's temperature has been increasing. Right? So the CO2 measurement the early start is from 1960s. I think 58 is the year really start. Is in this location. So everybody know where this one is? So it's in Hawaii. It's Mauna Loa. Like that is the start of the global CO2 measurement. Right? So that is from 1958. Right? So is a scientist, Dr. Kaling, right? So later you may heard of a Kaling curve, right? So that's the name after him because he initiated this program. This is a relatively remote island, far from major industrial sources. So that's why the data from here will be used as a kind of a global representative numbers, right? So since 1960s, the measurement has been continued on. Right? So that's you can see that's unfortunately the number has been continually increasing. Right? We already passed 400 mark in 2000-ish, and right now we are around 410-ish. And in this insert, so this one is a derivative. So that is basically the first difference between this year's number from last year's number. You get the rate of change. Right? So this is overall concentration change, and this is the rate of change. So you taking the difference between this year's number from last year's number. So two quick questions. What responsible for the zigzag? Why CO2 has this zigzag? What's the major reason for this? So when you have a peak here, that means that is the highest CO2 level within a year, right? Why that happens? So you can see the zigzag is annual trend. Every year you have a peak, so you have a valley. Yeah, it's a seasonal activity. What seasonal activity? Say that again. What? You mean human activity? Okay. So the zigzag is actually not human activity. It's not like, for example, some may think in winter you use a lot of heating, maybe you generate a lot of CO2, right? So sure, that's play a role, but not a major reason for this. It's not big enough. Any other guys are thinking? Did you try to say? So what's the major reason you said? Vegetation. Okay. Yeah. So yeah, that's exactly right. So when you think about the global carbon budget, right, how much carbon we emit, right? So like about 1/3 of that emission is actually taken up by vegetation. So they are actually the major player in terms of carbon sink. They take up that 1/3. Then another third is taken up by ocean, right? The ocean take another 1/3. And then the leftover 1/3 is basically used to increase our CO2 level, right? So that's basically the rough budget. And ocean really doesn't change that much in terms of their kind of seasonal carbon uptake. Really what happens here, the zigzag is the vegetation, right? So basically, if you have a winter time, vegetation stop taking up CO2, stop photosynthesis, so you have a peak there. And then, during the summertime, the valley basically means the vegetation has been very active during the peak summertime. They take up a lot of CO2 from the atmosphere, and then you have a valley here. So every year you have a peak and a valley because vegetation either active doing photosynthesis or don't, right? So that's why this zigzag happening. So yeah, it's because of vegetation, because of photosynthesis. And another thing is you can say we are not only the overall trend is increasing, the rate of increase, the ppm per year is actually still increasing, right? So that's actually kind of alarming, right? So it's not only that means, if this one is not zero, if the rate is not zero, that means, the curve is always up. But if the rate is actually still, you still produce more and more CO2 per year. So that means, the curve will be kind of exponential increase. So that's actually the problem we are facing right now. Right? So another question for you guys is, you notice, right, for later, like for all the greenhouse gas, we use a ppm, or ppb, part per billion, or even part per trillion, depends on the different greenhouse we talk. Like for methane and N2O, we'll use ppb, and for some trace gas, we use a ppt, even small, right? But whatever the unit we use is based on dry air base, right? So all the numbers you are reading here is the dry air base numbers. So why we use dry air base? What do you think is the reason we use the dry air rather than wet air? So yeah, why we use like a dry air based measurement for all the greenhouse gas measurement? You want to say something? So yeah, you are getting there. So you are talking about, try to produce the ideal condition density for like greenhouse gas measurement, right? But it is on the right track. But think about the dry air. What dry air means? What we get rid of? Water, right? Water vapor, right? So that's basically dry air mean, right? So why we use dry air? Because water vapor is actually a big component of our atmosphere, right? So it's actually, when you think about the CO2 ppm, right? So water vapor is probably like 1,000 ppm. It's actually very large number. But same time, it's actually variable. It's not everywhere you have the same water vapor concentration, right? It's quite variable, right? So if you don't get rid of them, your number will be get affected, right? So that's why we always get rid of water vapor from the greenhouse gas measurement, right? So because water vapor has a high concentration in the air, but also is spatially variable, right? So that's why you have to get rid of them before you make a measurement. So that is CO2. And the next powerful greenhouse gas is methane, right? So that's very similar in terms of the trend. So you can say methane is not having the zigzag, right? It's essentially, we'll see, methane has been level off for some years and then is picking up again, right? So far, compared to CO2 and N2O, methane has a larger uncertainty, right? So just because it has a lot of source and sink, we still try to understand that, handle that better. But in general, we know methane has been increasing quite dramatically. And also, when you look at the insert, that is the rate of change. So what this number tell us? I guess in terms of rate of change. So what's your conclusion you will get if you read a figure like this? So again, remember we talk about as long as the rate of increase is not zero, the curve will be increasing, right? So you can say methane, most of the years essentially the rate is above zero, right? So that means even the rate didn't change too much, it's more or less stable, right? But the rate is not zero. That means for sure we will see the methane concentration in the air will continue increase in the future, right? So here is a figure from a global methane budget is from program called is a carbon program. Try to have idea for the methane on Earth where they are, give us idea. But this one you can see actually there is a very large range for a lot of the process, right? So there is uncertainty is quite big. People still try to narrow down the process. So, but in general, basically this one, for the green ones, talking about the natural process, and the kind of orange color is more like a human activity, anthropogenic activity. You can see some agricultural waste is a big producer, and fossil fuel production from industry is also a player. But for methane, has a lot of the natural process. So, the big one, the big sink is actually from the chemical reaction in the air, but there are some other like natural sources from wetland, right? Wetland emission, and there are some from the agriculture like rice production. So I guess really just to give you an idea what are the relative players in terms of the methane production and the methane sink. Methane sink is really, the big one is actually from a chemical reaction, right? Very different from CO2, right? CO2 is the major sink is from vegetation, is from biological process. So it's different. So, but people still try to narrow down the uncertainty, try to get this number. It's still very active research for methane budget. So the number 3 major greenhouse gas is N2O. So what's the general trend for N2O in terms of overall concentration and also the growth rate, from the insert? What's the general trend here? It's not a tricky question. Yeah, just. Anybody want to? Increasing, decreasing, stable?
Increasing. Gradient is increasing. Gradient is constant, so concentration is increasing.
Okay. So, yeah, so basically, that's a pretty obvious, like an increasing trend, right? So, but also for methane, for N2O, the rate is not zero, it's above zero, right? So that means, is for sure will increase, but also there is a slight increase in the rate as well. So that means, it's increasing, but it's actually even up. It's not like a linear increase. It's actually the rate will be faster and faster, like similar to CO2, right? So that's. So what's the major source of N2O? Anybody know? What's the number one source of N2O in our atmosphere? Can you speak louder? Okay, so you talk about industry. Actually, for N2O, the major player is agriculture. So the largest producer of N2O is actually from agriculture. So that is the largest producer. So that's why, people try to develop different ways to try to reduce N2O emission from agriculture. Right? So that agriculture is the largest producer. So can you guys hear me okay? Okay. So far we talked about the three, like CO2, methane, and N2O. There are three major greenhouse gases, right? But in our atmosphere, there are actually some minor ones. Their radiative forcing is actually much more powerful than the CO2 or methane or N2O. But because they are trace amount, so we don't talk about them a lot, but they are actually very powerful. So you can see we are using the unit of PPT, that's a part per trillion, right? So remember, when we talk about the methane, that's a ppb, part per billion, right? And the same for methane. Methane and N2O is part ppb, and CO2 is ppm. And for them is a ppt, right? Part per trillion. It's a very minor like a component. But we still care about them because, so this our group called halogen native greenhouse gases, right? So basically, when you look at the element tables, right? So they are really from the halogen column, all of these gases, right? So the most famous one is the CFC, right? So that's one, the famous fault, they can destroy ozone in our atmosphere, but at the same time, it's actually a very strong greenhouse gas as well, right? So people use them for use for refrigerator, right? So as a coolant and the other things. So it's purely man-made, right? So it's not like naturally occurring, but people made this chemical to use for our purpose, and they realize it's actually become a very powerful greenhouse gas. So that's why people, and also this one, CFC is a carbon fluoride. So the fluoride part is very powerful, destroy like ozone layers, right? So that's why people try to eliminate them from atmosphere, right? And these two gases are the replacement for CFC, right? So that's why you can see CFC is actually level off, even like going down. But for HCFC and HFC, they are increasing because they are the replacement of a CFC. So I guess they are minor in terms of concentration, but because per molecular bases, they are very, very, very powerful. That's why right now people consider them as well. So for some other trace gas, we don't talk them too much, but they are actually used for like computer chips and other things. They're actually quite, you can imagine with modern technology, people rely on them a lot, and these gases exponentially increasing. Right? So right now, their concentration is relatively small, but they are very powerful greenhouse gas. So that's why people care about them. So for the CFC, that's actually the decrease is caused by the Montreal protocol, right? So to me, that is a kind of a successful story of environmental science, right? So that's we figure out the problem. We know CFC has been destroying ozone layers, and people then getting together, they signed the protocol, Montreal protocol, right? So they basically talking about, okay, we stop doing CFC, right? We find other chemicals like for the same purpose, and that's actually making the CFC lower, right? So that's actually a successful story. So like we talk about CFC, because the ozone, right? The ozone is itself is also greenhouse gas, but at the same time, ozone depends on where they are, right? So there are two major types of ozone layers. One ozone layer is in the stratosphere, and one ozone layer is a kind of man-made, is in troposphere, right? So for the stratosphere ozone, right, we typically use the Dobson unit. Right? Dobson unit, we are talking about under standard temperature pressure, you have a 0.01 milliliter. That is one Dobson unit. Essentially, we are talking about, essentially 1 milliliter is equivalent to 100 Dobson unit. So here, I give you a scale, right? In US, if you have a penny, so if you have two penny stacked together, that is a 3 milliliter. That is average depth of ozone layer in our atmosphere. So that is a good ozone layer. That is the one really helping us, right? Because ozone actually causes skin cancer, right? So they actually helping us for that. So this is from IPCC report talking about the ozone layer trend in recent years. So here is a global average, and then you have the kind of the different zone, different climate region, northern atmosphere, tropical region, and you have a southern atmosphere, right? And then polar region, right? So you can see their scale is slightly different, right? But it's around 300 Dobson unit. So that is the natural concentration for ozone. And you can see for northern atmosphere and the tropical ozone layer wasn't changed too much. Really, what happens the most is the southern atmosphere and the polar region. Ozone layer has been depleting very fast in the last 20, 30 years until recently becoming stabilized. Right? So that's because of the Montreal protocol. Right? So because we got rid of the CFC from our air. Right? So here just give you an idea for like UV layers. There are three types. Right? UVA, UVB, and UVC. Right? So they have different wavelengths, and basically the shorter the wavelengths, the more energetic they are. Right? For UVC and UVB and UVC, they are the really dangerous one, very energetic. Right? So ozone essentially can block most of the UVB and UVC. Right? Only like UVA can go through. Right? So that's why is less energetic, less harmful for us. So that's why the stratosphere ozone is very important. But again, like we talked about, for ozone, not only we have a stratosphere ozone, we actually human activity also create a troposphere ozone. Right? So that is a kind of a two story of ozone. One is a good one is a bad one. Right? So that is surface ozone or troposphere ozone. Right? So the x-axis is basically the trend, y-axis is latitude. So the trend basically we are talking about the kind of per decade, whether they are increasing or decreasing, right? So based on this, so these are the kind of ground measurement, these are the satellite measurement. And in more recent years, people have a satellite measurement for surface ozone. So again, ozone is a pollutant, right? It's man-made, based on, essentially from your, if you go to gas station, right? If you have a VOC come from the gas pump, if you are under a sunny condition, then you have a NOx coming from the pipe from your car. So it's a perfect condition, they will create ozone, right? So that's the ground level ozone. It's a pollutant. If you have a breathing issues, asthma, for example, it's very bad for your health. So that's why people monitor them, monitor the changes. So based on this type of measurement, what's the general conclusion? Like the ground level ozone is increasing or decreasing in recent decade? So again, all these figures are from IPCC report. I put the number here, right? So that's typically referred to the chapter number and then where they are if you want to go back to read the chapter. So, but one of the ideas is that you should be able to read their figures, try to guide what's kind of a major trend. So based on this type of figure, right? So for the surface ozone in the recent decade, is increasing or decreasing? It's not, so it's not tricky, right? So, you'll see there is a zero line here, right? So, basically if the number is on the zero line, on the left, negative, that means, the trend is decreasing, and if on the right, it's increasing, right? So basically what this one tells us, right, especially in the lower latitude, right, from, you can hear in northern atmosphere, that's the most industrial activity happens, right? So you can see it's actually the ozone concentration has been increasing in recent decades. So you can see here too, and that is also reflected in the satellite measurement. So there are some places that are decreasing, but for majority of the measurement people have is actually increasing. Right? So that's essentially this message tell us. Right? So in recent decade, the ground level ozone has been increasing. Right? So that's not good news for us, right? Because it's a pollutant, it's actually affecting humans' health, right? So that is a man-made ozone. So that's quite different from the stratosphere ozone. That's a naturally occurring ozone. That's actually protect us from the UV radiation. Right? Any questions? Okay. So I guess, the key point is make sure you understand there are two types of ozone in our atmosphere, right? So the lower level, like a troposphere ozone, right? So how high is the troposphere, roughly? I heard the number. 10 kilometers, right? So that is really kind of a rough height of a troposphere, right? So basically all the weather events, the storms, things happen within troposphere, right? So that's why airplane will fly above that, right? So you fly above 10 kilometers, right? So, so the troposphere ozone, right? So that's bad. That's a man-made ozone essentially, right? But another type of ozone is naturally occurring. That's in way above 10 kilometers, right? That's a stratosphere ozone, right? So that's good for us. That's actually protecting us. So the other things in terms of atmosphere chemistry, like changing the climate drivers, would be the aerosol. Right? So here we talk about aerosol. We talk about that is non-sea salt sulfate and also black carbon. Right? So essentially they are the industrial production. Right? So either black carbon or the sulfate is from industrial activities. So here are some basically satellite-based measurements, and they are the spatial average. So what's the general trend you can see in terms of the aerosol in the atmosphere? So there are regional differences. But in general, what's the general trend what's the major conclusion you can get? So yeah, okay, it's not, yeah, you can say like there are like different regions, right? So that's represented by different color, and then we talk about in the last 150 years. So there are different information there, but what kind of information you can get from this? Anybody want to try? Just describe what you found from the. You want to say something? So is that all increasing or decreasing? Oh, there. I guess basically you can say, right, so depends on where you are, right? So some regions you can say is actually continue increase. Some actually increasing and then start decreasing, right? So I guess you can pick the region, but the idea is essentially for the, like Europe, like for North America, right? So it's actually, they are on the similar trend. So they has been increasing dramatically until maybe 1980s, and then there will be sharp decline. So the same, you can say the Europe like this, and Greenland is affected by Europe as well, right? So Eastern Europe like this. So essentially for the industrial world, right, or Western world, so historically there has been very dramatic increase in their aerosols because of all the industrial activities. But in recent years, they have a sharp decline, right? So, but the pattern is different for developing country, right? So here you have South America. Yeah, somehow for this report, like East Asia is not here. Actually, East Asia is very similar, like India here, like China is actually all similar to South America. It's actually still like a sharply like an increase, right? Just because of the industrial activity is quite strong, and the environmental regulation is not as strict as in Europe, right? So you can, if you look at the global map, you can actually see that, right? So that's in the last 20 years. Right, from 2000 to 2019, you can see for like a US, for like a Europe, right, so it's a grid, right? So that means their aerosol, that is aerosol optical depth, right? When you look at from the satellite, from space, like all the way through the color, so you can see is actually decreasing. But when you look at like East Asia, right, here India and part of Africa, you can see they actually still under like an increasing trend, right? So there are actually regional differences essentially, right? So if you, some part of the world is actually still continue increasing, but many other part is actually increasing and then stop and decreasing quite dramatically. So, one of the major reasons for this decrease is actually through the environmental regulation, right? So in US and in Europe, right? So from the 70s, they actually start passed the Clean Air Act, right? So that's first started in 1970, and then there is an amendment 1990. So it's very similar for Europe as well. So they actually passed similar type of law, and this law, two things are very relevant to the aerosol. One is a mandate for all the cars; they have to equip with some of catalytic converters, right? So that's why you can actually convert all the carbon monoxide to and hydrocarbon to carbon dioxide, right? So that's why it's more from the public health point of view. You don't get poisoned by carbon monoxide, right? If the combustion is not complete, you will have the issue with the carbon monoxide production. So that's one of the mandate from the Clean Air Act. So the another one more relevant to like aerosol reduction is actually for the power factory or for the anyone use smoke stacks. So one of the requirements for them is after they burning things, they have to basically install the scrubber, like things like this. So the idea is they use carbonate calcium, so that's react with sulfur gases and then produce gypsum, right? So that's basically the material of the walls, dry walls, right? So that's a gypsum, right? So the idea is they go through a serial process. They settle down the gas, like the big particle already settled down, and then the leftover will actually passing through a scrubber to be able to get rid of all the sulfate aerosol. So that's become very effective, right? So that's why we talk about in Europe and in US. So essentially there is a huge reduction in the aerosol, right? So that's it's very good for the human health point of view. So that is the main reason for the big reduction in recent years. Any questions so far? Okay, so far what we talk about here right now is really talk about kind of the drivers, right? So we talk about the solar activities, the volcano activities. They are not really the major driver, right, for the observed warming, right? Really the observed warming is through the greenhouse gases we produce, right? So the major player is CO2, but methane, N2O, and the halogen gases, they are all responsible for the greenhouse warming. Ozone is also a very important player as well. Right? So aerosol, again, that is the only major cooling force in atmosphere, right? So that one, essentially there are regional differences, right? So some places are decreasing, some places still increasing, right? But we can't rely on aerosol to cool our climate because, even they are cooling the climate, but they are not good for our health, right? So it's not good for our breathing, right? So that is a problem. You can't rely on them, even they are cooling, right? So far, what we talked is really the drivers of climate change. And then next few slides we will touch on is basically we'll talk about the kind of the trend, overall trend, right? So what the Earth's temperature look like and the detailed information about that. So this is a figure from IPCC report. So that is a kind of the Earth's temperature in deep time, right? So deep time we are talking about 60 million years old, right? So remember when we talk about CO2 concentration in deep time, that is a time when CO2 concentration has been declined, right? So you can say, even without you can actually have a good mental linkage between CO2 concentration and the temperature trend in our Earth's history, right? When CO2 concentration has been declined, Earth's temperature has actually been declined quite fast. And also, this one is pretty interesting, like give us kind of the brief history of different things, right? For example, when agriculture started, right? About maybe 10,000 years ago, right? So that's agriculture time scale. And then when we think about ice sheets, right? So ice sheets is really the largest ice on Earth. That's only appear in Antarctic and in Greenland. Only 2 places has ice sheet. Right? So you can say give you the time scale of where ice sheet actually start. Right? Ice sheet is start like about 30 million years ago. Right? So that's East Antarctic ice sheet, and the West Antarctic even later. Right? So that's tell you like how old the ice sheet on Earth. So just to give you kind of that's when humans as a species actually start. Right? So that's give you a relative time scale, like when agriculture start, when ice sheets on Earth start, and how the relative change was in general the trend of a temperature. You can say like in the Earth's history, right? So there are times much warmer than what we have right now. Right? So we're talking about 15 degrees C, like above the pre-industrial period. But remember, that's a very different time, right? So there's no human on Earth. There's not even ice sheet on Earth, right? So it's very different. So that's just give you a kind of a perspective from deep time, how Earth's temperature has been evolved. And for modern time, right? So when we talk about surface temperature, so the idea is there are 2 different ways. When you read literature, you probably heard GMST or GS80, right? You need to know, okay, what they actually talking about, right? So GMST is actually referred to global mean surface temperature, and GS80 is a global surface air temperature. And so really, you can say the difference is one is called global surface temperature, one is called global air temperature. Right? So the main difference between these two is really the ocean part. And for both data set, people use the land surface air temperature, SL80. Right? So these are the same between these two. Really, the difference is how people measure ocean temperature. Right? One of the data set, people will measure sea surface temperature, SST. Right? For another one, people use marine air temperature, M80. Right? So this is surface temperature, this is air temperature, right? So they are different, right? So like if you go to desert, right? So the air temperature may be like 40 degrees, but if your bare hand, touch the sand, that's 70, 80 degrees, right? So there's actually huge difference between air temperature and the surface temperature, right? But for ocean, the difference is not that big, but there's still a difference there. So, but that's why we have 2 types of data set. Like when we talk about the global temperature change, some people use surface temperature, some use global surface air temperature, right? So, but when you look at, again, just like anomaly, right? Like when we think about the trend, regardless whether you use some use GMST, some use GS80, when you compare the change between different periods, what kind of conclusion you can get here? So I'm talking about this table. So that's we are talking about different period, right? You compare these 2 periods or these 2 periods, and then how temperature has been changing based on different data set. What's a general conclusion you can get from this comparison? So for the trend between global mean air temperature or global mean surface temperature, when we look at the trend, are they same or are they different? So if I use, for example, global mean surface temperature to, to calculate kind of the trend or the change in different period, compared to if I use a different data set, if I use global surface air temperature, whether I will get the same conclusion or not. Based on this, what's your conclusion? So I heard same. Same? Say that again? Same, right. So, yeah, I mean, this is the same, right? So like we mentioned, the temperature itself could be different, right? So, air temperature, surface temperature, and air temperature, they could differ, right? So, but when you look at the comparison between these two, that's changes, right? So they almost spot on, like almost exactly the same. So basically, when we talk about the change, it doesn't matter which data set you use. It actually give you the same conclusion. So again, like anomaly, if you use a different thermometer, right? So maybe the absolute number is different. This thermometer maybe give you a little bit higher number. This give you a lower number, right? So, when you compare these two numbers, sure they are different. But when you use this same thermometer, you measure the same thing, like time by time again. You look at the difference, the change. They are same because the difference cancel out, right? So the same idea for the two data set, right? So you can use any data set for calculating the trend. That's give you confidence to show, okay, I can use any. It's actually give me the same trend. Give us confidence about the trend we observe, right? So that's a good thing. And this one is kind of surface temperature trend, right? So this is from 1900 to 1980. And this one from 1981 to 2022. So that's a global temperature change. What major conclusion you can get, when you compare these two? In general, anything like come up in terms of spatial distribution? What's the kind of the take-home message you can get from this? There are a couple of things, right? Very. Can you say that again? I didn't. Oh, sorry. Yes, there are significant changes. Yes. So I guess more specific, if you compare these two maps, or like talk about one map, what kind of the features you can comment on? So maybe let's say spatially, what kind of a major conclusion you can get? So I guess your point is almost like everywhere is warming, right? So that is a major conclusion. Yeah, that's one key message you can get from this. But there are other information here, right? What other information you can get? Variability. Oh, okay, yeah. So the other is the spatial variability, right? So you can say polar region actually warming much faster, right? So the rate is much faster. They actually get impacted much significant than other region. Yeah, that's a very important message here, right? So sometimes people call them like vulnerable regions, right? So yeah, that's definitely. What else? I guess if you compare these two, right? So that's a different period, right? From 1900 to 1980, right? So that's they are using the same scale of change. What that tell you? right? The rate has been accelerated, right? So you can see here we're talking about 80 years of change, and here is only like 40 years. And but the changes we saw here is already bigger than the 40 years of change, already much bigger than the 80 years of change, right? So the rate has been accelerating much faster. Anthropogenic activity. Yeah, I mean, you're talking about the reason why that happens, right? So yeah, essentially, yeah, exactly. That's pretty much all the greenhouse gas emission we produce. We talk about the CO2 growth rate has been accelerating, right? The growth rate not only not zero, is actually accelerating, right? So that's really the major reason responsible for the kind of the faster change, right? So yeah, again, yeah, there are a couple of important messages you can get, right? So the rate of change is accelerating, and also, you know, there are spatial variability, right? The polar region actually got affected much more severe than other region, right? But also, like a spatial variability, but also time variability, right? So yeah, I guess that's what we know in terms of a global distribution. And if we average them together, right, like average all the pixels together, that's actually what we saw in terms of the land and ocean trend. So red is the land trend, the blue is ocean trend. What does this one tell us? Sure. So you're talking about why this region got affected more than other region? Is that your question? Okay. Yeah. So remember when we talk about the climate variability itself, different regions naturally they are different. There are some inherent features there. So for example, for polar region, right? So they have a lot of sea ice, seasonal sea ice there, right? So remember for sea ice changes is actually positive change, right? So you actually they are actually most vulnerable to temperature change, melting the sea ice, and they actually accelerating the change because of albedo change, right? So that's basically why that's the inherent feature of that region actually responsible for that. Yeah. Yeah, that's a good question. So when we look at this one, the land and the ocean, so what's the major conclusion you can get from this one? Yes, it's not like a tricky question. Really just try to let you to raise a figure and interpret the results. Can you be louder? I heard somebody talking. Right. So I guess your comments on the difference between land and ocean, right? Yeah. So yes, exactly. So basically, we know both land and ocean, they are actually increasing. The temperature is increasing, right? That's one message we can get. But also you can say the land temperature increase almost double the ocean, right? So the rate of increase is actually not the same, right? Land warming much faster than ocean, right? So that's because ocean has a much bigger heat, like a buffering capacity, right? So but ocean definitely is still warming, right? So if your IPCC report has a special chapter just for ocean, talk about ocean heat content, ocean salinity, how things are changing. But in general, we know land and ocean are different. The rate of change are different, right? Land is just warming much faster than the ocean, right? And then if you average this, get a global average of temperature change, right? So that is basically the surface temperature change. And this one is a decadal change. Every 10 years, how things are changing, right? So I guess, all of this are not surprising. We know, like, the Earth's temperature has been increasing, right? So the most warmest years in recent decade, right? So it's becoming warmer and warmer, right? So that's a key message. So, this is when we talk about global warming, right? We really talk about the troposphere, right? So the atmosphere we live in, right? The lower atmosphere. But sometimes we don't talk a lot about stratosphere, right? So that is upper atmosphere trend, right? So that's also in IPCC report. So that's give you the global trend, different stage, but also tropical region in terms of a troposphere. In terms of stratosphere, right? Again, we talk about stratosphere. That is we are talking about is much higher, right? So that's between 0 and 10. That is we consider troposphere, and above 10 roughly, right? That's the stratosphere, right? Based on this one, this trend, or you can look at this as well. But in general, what's your major conclusion for the stratosphere temperature trend? So again, that's the x-axis is temperature trend. You have a 0 and then negative and the positive numbers, and the y-axis is height, right? The altitude. What's a general conclusion you can get? Let's just say, like they all tell us similar story. Let's just talk about the first one here. That's true. As you go up, as temperature decrease, right? But here we are talking about we are talking about the temperature trend. That's a temperature per decade. We are talking about in 40 years how things has been changing. So what kind of major conclusion you can get from this? So the stratosphere temperature is increasing or decreasing? Yeah, you can talk with your neighbors, discuss, and then get it. Remember, we talked about the temporal trend, right? So not the spatial trend. So any question about the figure? How do you read the figure? Okay, I guess for the sake of time, we'll talk about this, right? So, like you guys mentioned, right? If you look at the height profile, sure, they're always warmer in troposphere and then colder in upper atmosphere, right? So that's kind of the vertical trend. But we are looking at is in the last 40 years also, what is the general trend? You can see for troposphere, right? So that's above 0. That means that's warming, right? Temperature is increasing, right? So when we talk about global warming, we actually talk about the troposphere, right? So that is a layer we talk about, right? But the ones we don't talk about a lot is actually the upper atmosphere, right? About 15 kilometers. You can say it's actually global cooling, right? Stratosphere is cooling, right? So that's because the number is negative, right? So, like in the past, so this one tell you a similar story. Is kind of a spatial average, right? So you can say, depends on where you are, but in general, like a lower atmosphere is right, is a global warming, right? So if you move up, you can say it's actually cooling, right? The stratosphere is actually has a cooling trend. So, in the past, the climate denier will say, we have a cooling happening, right? Why we say that's global warming, right? So, that can trick people, right? So, but in fact, right, if you, know the meteorology, that's exactly what we expected, right? The cooling trend, right? So because why global warming, right? So because, we have a CO2 and other greenhouse put a layer, right, in our atmosphere, lower atmosphere as a blanket. All the heat actually got trapped here, right? So that's warming us. So because all the heat trapped here, you can imagine, right? So there will be less heat like here. It becomes slower like a cooling, right? So that's just the net energy balance, right? So I guess, for you, really just try to make sure you understand it, right? So when we talk about global warming, we really talk about the troposphere part, right? So, in the stratosphere actually is cooling, right? So that's very interesting, right? So, the boundary between troposphere and the stratosphere, roughly is 10 kilometers, but it's not like a uniform everywhere. Somewhere will be a little bit higher, some be a little bit lower, right? But global average is maybe 10 kilometers-ish. But the thing is that there are meteorologists has been studying how this boundary has been changing, right? So their main conclusion is actually IPCC report here didn't talk about this, but in general, what we know is this boundary has been moving up slowly, right? So that's actually, part because of the global warming as a consequence. So what do you think the consequence that will be if the boundary move higher and higher? What do you think that will happen to us in terms of taking airplane? This Nature paper actually specifically talk about this. So basically that means your air ride will be much more bumpier, just because all the weather conditions happen in troposphere, right? If the height becoming higher in the future, because if the plane doesn't change their attitude for flying, that means all weather pattern will become higher and higher. There will be a lot of bumpiness in the flying, right? So that's will be, right, if an airplane doesn't really keep become higher and higher. So, to me, it's just very interesting to think about how climate change could affect many aspects of our life, right? So, questions? Okay. So, so far we talked about really the kind of the temperature profile, temperature part. So the next few slides we'll talk about water aspect, right? So, when we talk about first we talk about the humidity, right? The humidity in the air, right? So, as we all know, there are different definitions for humidity, right? So, one definition is a specific humidity, right? So, that's by definition really talk about absolute amount of water vapor in the air, right? Either per weight or per volume. That is a specific humidity. And the other type of humidity representation is relative humidity, right? So that's relative humidity is the ratio, basically is the actual amount of water vapor in the air divided by the saturation amount of water vapor in the air, right? So that's why we call relative humidity. So really, so this one is how much actual water vapor there, and this is in theory under that temperature what's the maximum amount of water vapor the air can hold, right? So that's the ratio we call the relative humidity, right? So the amount of water vapor can hold is, you can say based on this equation, we know is an exponential equation. That means the higher the temperature, the air temperature, the more water vapor the air can hold. Right? So, the higher the temperature exponentially, the amount of water vapor the air can hold exponentially increase with air temperature. Right? So that's what this equation tells us. So that has a consequence when we talk about the changes in specific humidity and relative humidity. So here is a global trend for the changes in specific humidity, and this is a global average, and this is relative humidity, and this is a spatial distribution. So let's, for now, just forget about the spatial distribution, look at the global average. So what's the general trend here? What is the trend for specific humidity? What's the trend for relative humidity? And why you think that's the case? Let's one step ahead. Let's like a first step. What's the general trend for specific humidity? Increasing or decreasing? Specific humidity. Increasing, right? Yeah. So this one is a specific humidity, right? So that is the absolute amount of water in the air. So you can see that is increasing, right? So different data sets basically show you the same trend, right? So that's not surprising, right? So higher temperature, like more evaporation, right? So there are more water vapor in the air, right? So that's why specific humidity is increasing. And how about relative humidity? It's decreasing, right? So, there's different data sets have different degree of a decreasing, but in general they show like a decreasing trend. Why you think relative humidity is decreasing? Data set from UK and JPCC, right? So that's from US. So there are different data set, give you the kind of the rainfall pattern. Depends on how much interpolation they do, right? So some has a higher interpolation than other data set. But in general, that's a global trend, and this is a global average across all the grid cells. So what's the general trend you will see in terms of precipitation at a global scale? Let's really just focus on this one. So is it increasing or decreasing? Or no change? Can you say louder? Slightly increase, yeah. So yeah, basically for precipitation, essentially for most of the part, right, in the last 100 years, it's not really changed too much. But in recent maybe 20 years, right, slight increase, right? So that is the global average, remember, right? So, precipitation has a lot of regional differences, right? So there are actually some places they have a bigger increase, some places they actually decrease, right? So a lot of people use like a drier part getting drier, wetter part getting wetter, kind of like a description, right? So that's more or less correct, right? So in the wetter climate, their increase is actually bigger, and in drier place they tend to decrease. And then average out overall is a very small increase overall. So, but for precipitation, right, later we'll talk about that, right? So it's not only total amount matters. Sometimes how the precipitation delivered is also matter, the frequency, right? So because right now the general trend is a lot of time when you look at the place, the total amount of water they receive doesn't change, but the storm become bigger. Essentially that means the same amount of water just come like in couple of big events, right? So that's not good for agriculture, not good for vegetation growth, right? So later, I will talk about that when we talk about the science part. So that is a kind of a global precipitation trend. Just give you the idea. That's all from IPCC report. Give you the kind of global distributions and also global average. So the last couple of slides, we'll talk about this is a stream flow, right? So essentially what IPCC tell us is they basically have a low confidence in terms of global trend for stream flow, right? So just because, some places you have a very dense network for stream flow measurement, like in US, like USGS monitoring very large network for the stream flow measurement. But in many parts of the world, a lot of stream are not gauged, right? So nobody measures their stream flow. So part of the reason for that, part of the reason, you don't have a global coverage, and then you have low confidence for the global stream flow. But in general, people find is there are more places they actually show you decreasing trend. But we just have a low confidence because of data scarcity. So that is for the stream flow. Yeah, I have a couple slides for large scale circulation, but I think we could just stop here. Yeah, I guess if you are interested, we can talk about it later. But like for large scale circulation, we talk about Hartley cell, like Hartley circulation, and the worker cell, worker circulation, right? So how they are changing, like what we know about them, and how do they impact our climate system. But that will be, we kind of run out of time for that. But in general, I want to emphasize one thing is, worker cell, right? So that's actually happened. That's from a British scientist, Walker, Dr. Walker, right? So he actually did his field observation in India, right? So actually discovered the worker cell, right? So that's actually very relevant to this continent, to you guys. And also, worker cell is very relevant to El Nino events, right? So if you have a stronger worker cell, that means you have a La Nino events. You have a weaker worker cell, you have a El Nino events. So, but I guess that's more like large scale circulation. We won't talk about that. But if you are interested, we can talk separately. So, any questions for the content we covered so far? We cover quite a bit of stuff. I just want to make sure you got most of the stuff we talk about. Any questions? You're good? Okay. So yeah, go ahead. So you said the drought has been increasing. Can you repeat your question? Sorry, I don't think I still. Yeah, can you come closer, be louder? Yeah. Polar region, you mean? Yeah. Yes. So yeah. Yeah. So yeah, I mean it does, right? So you're talking about the polar region. Yeah, the rainfall change there is bigger. It's become more like rainfall there, more flooding there. Whether climate change responsible for that, right? So yeah, I think so. Yeah, because just more warming, more ice melting, you change the local climate, becoming wetter. Yeah. Right. Arctic, I mean, I think because of the Arctic ice cover, like seasonal changes, it's definitely get affected by the warming as well. Yeah, that's should be very similar to. I mean, the ice is very different. One is a permanent, like in Antarctic is a very thin ice, and the Arctic is very thick ice, right? So, but they are still ice. They melted and they changed the local climate. Yeah, it's quite higher. It's quite thicker, right? Yeah. It's more multi-year sea ice. Antarctic is more like an annual sea ice, right? So yeah, like shallow, sure. Any other questions? Okay, all right. Thank you, guys. I guess we'll take a break, right? So then we'll actually go to the next section about the tutorial. All right. Thank you.